Okay, thanks everybody for staying for the last talk of this day. I will try to keep it not so technical, you're probably tired. Okay, so this is a joint work with Noga Alon and Amir Yehudayoff, and it's about sign rank versus visit dimension. Okay, so maybe the motivation for this talk is studying the universality of linear classifiers. So which problems can be learned by a linear classifier? So linear classifiers are algorithms that use half spaces to classify. So perceptron, SVM, kernel machines, etc. And these algorithms are applied in many contexts. And the question we try to study is which problems can be learned by a linear classifier. So for example, given a problem, can we always generate features under which the problem become linear? Okay, so this is on a very high level. Now let me get a bit more specific. So first, what are linear classifiers? And here I describe the realizable case. So the linear classifier is an algorithm that gets as an input two linearly separable sets in a Euclidean space. And the output is a hyperplane that separates these two sets. So for instance, the red points can be one set, the blue points can be the second set, and their algorithm may output this separating hyperplane. Okay, so as we defined it, linear classifiers only apply when the concept class is of half spaces. But we want to ask for a general concept class that is not necessarily a geometrical one. So how can we use linear classifiers when C is some arbitrary class that is not necessarily geometrical? So the answer is that we represent C by half spaces. What does it mean? So a representation of C by half spaces is a mapping from the domain of C to a Euclidean space such that every concept in C becomes a half space after we apply this mapping. So the points that are labeled by 1 and the points that are labeled by 0 are linearly separable. For example, we may consider this simple class of only 3 functions, and the domain contains 5 points, A, B, C, D, and E. And here we have a representation, a mapping that takes any point to the plane. And indeed, each hypothesis corresponds to a half space. So for example, the C1 labels A and D by 1 and the rest of the points by 0, and they're indeed separable. And the same goes for, okay, so this is a representation of a class in a Euclidean space here in the plane. So this brings us to the definition of sign rank. So the sign rank of a class C is the smallest dimension in which C can be represented. Okay? And indeed, low sign rank implies good generalization bounds. So how can we learn C? We just apply a linear classifier on its representation in the space. And one example where we have such representation maps are kernel machines. Right? So a kernel machine uses inner product, which is implicitly uses a representation in a Euclidean space. And okay, so, but in fact, theory also gives us the concept of margin. So we know that if we have a representation, perhaps in an infinite Hilbert space, with a large margin, then they also imply good generalization bound. But large margin representation can be projected to low-dimensional representation by standard techniques like Johnson-Lindenstrass, random projection. Okay, so to conclude this part, good generalization bounds for C by linear classifiers imply that it has a low sign rank, a low-dimensional representation. And the question that we consider, given this informal corollary, is which learnable classes have small sign rank. Okay, so we're going to discuss 2 complementing results for this answer. The first one is perhaps bad news, that some, and in fact many, most of them, learnable classes have a very large sign rank. So for every D, which is at least 2, there is a concept class with domain of size n, with this dimension D, so it's learnable by D examples, but the sign rank will be n to the omega of 1. And the D is at least 2 is necessary, because if the this dimension is 1, then you can always represent it with in dimension 3. And this strengthens a result by Ben David, Aaron, and Simon that gave a slightly weaker bound only for D, which is at least 4. So this is the interpretation of this result is the weakness of linear classifiers. Yes, so it means that there are classes with this dimension just 2 that have no representation in R to whatever number you take, 10 million, or representation with margin that is at least 1 over 10 million. Okay, the second result is that for every learnable class, the sign rank cannot be too large. More formally, for every fixed D and every class of this dimension D, the sign rank is at most sublinear in the size of its domain. And this upper bound almost matches the lower bound I stated before, and we can interpret it as fitness of linear classifiers, because it says that every learnable class can be represented in some non-trivial way in a Euclidean space. And in the paper, we discuss how such representations are useful for learning. And informally, it's because they imply non-trivial compression. You have each concept is defined over a domain of size n, and you embed it somehow in a Euclidean space of size sublinear in n. Okay, so to wrap up everything, we said that generalization bound for learning C by linear classifiers imply low sign rank, and then we had two complementing results. One, that there are classes with learnable classes with large sign rank, and the second one that every learnable class has at most sublinear sign rank in its domain. And yes, and just one more remark, that we use ideas from these results in the paper to get other results, other corollaries in different fields, because both the sign rank and VC dimension have important roles in other fields. So, for example, we're able to answer open problems that was posed by Peter Frenkel in '89, and another open problem from Ben David, Aaron, and Simon from 02. In geometry, we extend the separation by Gartner and Welzel. We also considered the problem of computing the sign rank, and we showed that it is in fact harder than NP to compute it exactly. It is equivalent to the existential theory of the reals. And we also give a non-trivial approximation algorithm for computing it. Okay, so thanks.